In section 8.4, we discussed the gas laws. The gas laws are a series of mathematical relationships between the different parameters that characterize a gas. Gas laws describe the relationship between the pressure of the gas, the amount of the gas, which will always be in the SI unit of moles, the temperature of the gas, which will always be in the SI unit of Kelvin, and the volume of the gas. It's worth noting while we're getting started here in defining some terms that standard temperature and pressure, often abbreviated to STP, refers to a temperature of 273.15 Kelvin and a pressure of 1 atmosphere. So if you do see those letters, STP, then you automatically know the pressure of your gas and its temperature. The first gas law that we're going to learn about is Boyle's law. Boyle's law describes how pressure and volume are related if all of the other parameters are kept constant. What is observed is that volume is inversely related to pressure. What this means is that the volume goes up as the pressure goes down, or the opposite, the volume goes down as the pressure goes up. Mathematically, Boyle's law is often written like this, and that's read as pressure is inversely related to the volume, or it's written like this in terms of a formula: the initial pressure of a gas multiplied by its initial volume is equal to the final pressure of a gas multiplied by its final volume. Now, that's a bit of a mouthful, so sometimes people will abbreviate pressure initial as PI, volume initial as VI, pressure final as PF, and volume final as VF, or in place of the I and F, they'll use 1 and 2. So we start at 1 and we end at 2. So you kind of see a variety of ways in which Boyle's law is written if you're looking at resources on the internet. So here's an example problem where we're using Boyle's law from the book. It says if a sample of gas has an initial pressure of 1.56 atm, so let's take a note of that, and an initial volume of 7.02 litres, so volume initial is 7.02 litres. What is the final volume? So V final is what we're trying to find if the pressure is reduced to 0.987 atm. So pressure final equals 0.987 atm. So I always like to write out the formula symbolically. And then we want to reorganize to solve for VF. So I'm going to divide both sides by P final. Let's tidy that up. And then now I can just put my numbers in. So V final is equal to pressure initial, 1.56 atm, times by volume initial, 7.02 litres, divided by P final, 0.987 atm. You can see that atm cancels out, leaving me with litres. So my final volume, see what we've got here, 1.56 times 7.02 divide 0.987, and that ends up being, everything there is to 3 significant figures, 11.1 litres. So the pressure went down and the volume went up, which is consistent with Boyle's law. So Charles' law describes the relationship between temperature and volume. Experimentally, it's observed that volume is directly related to temperature in Kelvin. What that means is, as the pressure increases, the temperature increases, or vice versa. So as the pressure goes up, the temperature will go up. As the pressure goes down, the temperature will go down. Mathematically, Charles' law is often written like this, which is read as volume is directly related to temperature, or symbolically, it's written in the equation like this: V initial T final equals V final T initial, which is sometimes written as V1 T2 equals V2 T1. So here's an example Charles' law problem from the book, and the important thing to remember is that your temperatures must be expressed in Kelvin. So it says a gas sample at 20 degrees Celsius, so I'm going to let that be T1, and I'm going to immediately turn it into Kelvin by adding 273.15. Has an initial volume of 20 litres. So the volume that goes with that is 20 litres. And we've got what is the volume. So V2 or V final is what we're trying to solve for. If the temperature is changed to 60 degrees Celsius. So T2 is going to equal to 60 plus 273.15, which equals 333.15 Kelvin. So symbolically writing everything down, we can say V1 T2 is equal to V2 T1. And then to get V2, we have to just divide both sides by T1. So V1 T2 on T1 is going to be equal to V2. So there we go. All right, so V2 is equal to V1, which was 20 litres, times by T2, which was 333.15 Kelvin, divided by T1, which was 293.15 Kelvin. So when I cancel my units, the Kelvin disappears, leaves litres behind. So let's see what we got here. 20 times 333.15 divided by 293.15. And so to three significant figures, I end up with 22.7 litres. So what did that mean? It meant that as the temperature went up, the volume also went up, which is consistent with Charles's law. Here's another example from the book. We have an initial temperature of 35 degrees Celsius, which I'm going to convert to Kelvin straight away. So 35 plus 273.15, 308.15 Kelvin. We have an initial volume in this case. It says a gas sample at 35 degrees has an initial volume of 5.06 litres. It says what is its volume? So we're trying to solve for the final volume. If the temperature is changed to minus 35 degrees Celsius. So T final will be minus 35 plus 273.15 Kelvin. So it's getting colder, so we're expecting our volume to go down. So when we finish the problem, we're going to check that our final volume is less than the initial volume. Alright, so V initial T final is equal to V final T initial. So V initial T final over T initial is equal to V final. So let's put that into the calculator. V initial is 5.06 liters. T final is 238.15 Kelvin. And T initial was 308.15 Kelvin. The Kelvin cancel out, leaving liters, which are appropriate units for volume. Putting this into the calculator and rounding to 3 significant figures, we get 3.91 liters. So what we found was, as the temperature went down, the volume also went down, which is consistent with Charles's law. So our answer makes sense. We can combine Charles's law and Boyle's law together to make what is called the combined gas law. So if you look at the combined gas law, you'll see that there are 1, 2, 3, 4, 5, 6 different variables in there. So what we're really saying is, if we know 5 of the variables that are in this equation, we can always figure out the missing one. So here we go. It says a sample of gas has P initial 1.5 atm, V initial 10.5 liters, and T initial 300 Kelvin. We're asked to find the final volume if T final equals 350 Kelvin and P final equals 0.75 atm. So let's think about what's happened here. The pressure has gone down, which will make the volume go up. The temperature has gone up, and that will also make the volume go up. So the final volume, whatever it is, must be bigger than our initial volume of 10.5 liters. So let's write out the combined gas law. PI VI on TI is equal to PF VF on TF. And we want TF, so we need to divide. We want VF, so we need to divide both sides by PF. And multiply both sides by TF. And there we are. So that's what we need to put into our calculator in order to get our final answer. So now we're just going to very carefully put our numbers in, trying not to make a mistake. And the important thing here is make sure you put both the top and the bottom line in parentheses. So VF is going to be equal to PI, which is 1.5, times VI, which is 10.5, times T final, which is 350, and then that has to be divided by TI, which is 300, times PF, which is 0.75. So when I do that, we're looking to get a number that makes sense. And seeing as both of the things that we were doing were going to make the volume go up, we're looking for a number bigger than 10.5. Let's see what we get. And I got 24.5 liters. And so that makes sense to me because I made the pressure go down and I made the temperature go up, and both of those things are going to increase the volume of our gas. Here's another one. We've got Pi equals 0.768 atm. We've got Vi equals 10.5 liters, and we've got Ti equals 300 Kelvin. In this case, we're asked what is the final pressure. So P final is what we're looking for. We know that V final is 7.85 liters and that T final is 250 Kelvin. So the temperature goes down, that'll make the pressure go down, and the volume has gone down, so that'll make the pressure go up. So unfortunately, we're not going to be able to estimate whether our final pressure should be bigger or smaller than our initial pressure, because we've got kind of two opposite changes occurring. So let's do the math. Pi Vi on Ti is equal to P final V final on T final. So we want P final, so I'm going to have to multiply both sides by T final, and I'm going to have to divide both sides by V final. There we go. That'll give us our expression. Okay, so remembering to keep everything in parentheses on both the top and the bottom line, we can go ahead and solve now. So P final is going to be equal to P initial, which was 0.768, times V initial, which was 10.5, times T final, which was 250, put all of that in parentheses, divided by T initial, which was 300, times V final, which was 7.85. So P final equals, parentheses, 0.768 times 10.5 times 250, divide, parentheses, 300 times 7.85 equals 0.856. And the units there will be ATM to match P initial. So the pressure went up a little bit. The last gas law that we'll learn about is called the ideal gas law. And the ideal gas law relates all four parameters that characterize a gas in a single equation. And the ideal gas law is PV equals nRT. So in this equation, P represents pressure in ATM, V represents the volume in liters, N is the amount in moles, and T is the temperature in Kelvin. The R is a constant called the universal gas constant, and it's equal to 0.0821 liters atmospheres per mole per Kelvin. So typically in an ideal gas law problem, you'll have some of the parameters defined, but one will be missing and you have to solve for the unknown parameter. So let's see what we've got here. P, V, N, and T. It says what is the volume in liters, so that's what we're looking for, of 1.45 moles of a gas at a temperature of 298 K and a pressure of 3.995 ATM. So let's write out the ideal gas law, and then we need to reorganize and solve for V. So we're going to have to divide both sides by pressure. And then now we can just solve. So we've got 1.45 times 0.0821 for R times by T, which is 298, divided by P, which is 3.995. So our volume, and the ideal gas law always returns litres, will end up being 1.45 times R, which is 0.0821, times 298, divide 3.995, and our volume is to 3 significant figures, because 3 is our smallest number of sig figs here, 8.88 litres. And that's a typical ideal gas law problem. We have 3 of the 4 parameters, and we're going to reorganize and solve for the 4th one. The only thing we have to remember is the value of R, and that's always given to you. Here's another one. It says cyclopropane is a gas that formerly was used as an anesthetic. How many moles of gas are there in a 100-litre sample if the gas is at STP? So standard temperature means a temperature of 273.15, and standard pressure means a pressure of 1 atmosphere exactly. The volume here is 100 litres, and our job is to figure out how many moles we have. So let's go ahead and do that. PV equals nRT, so I need to divide both sides by RT. There we are. So N equals PV, which is 1 times 100, divided by RT, so R is 0.0821, and then T, 273.15, because we're at standard temperature. So this is going to be 100 divided by 0.0821 times 273.15. And so our answer is, I'm going to give this to 4 significant figures, 4.459 moles. Okay, and that concludes Chapter 8.